Hello friends, welcome back to my YouTube channel. In this video, I am continuing my discussion on distillation. It will be 25th part of that discussion. And today I'll continue my discussion on McCabe-Thiele method because since last few videos, I have been talking about the McCabe-Thiele method. Today I'll talk about the thermal condition of the feed to a typical tray column. And then I will also talk about the parameter Q that is used to define the thermal condition of the feed to a typical tray column. To begin with, we will understand the operation of a typical tray column. Tray column is a cylindrical vessel that has multiple trays in it, multiple plates in it. Each plate, it acts as a device where liquid and vapor phases, they are brought in contact with each other. Feed is admitted on a tray that is located centrally. We call that tray as the feed plate. The liquid portion of the feed, liquid part of the feed, it will be flowing down. It will be taken out at the bottom. It will be heated in the reboiler. The resulting vapor phase, it will be admitted at the bottom into the column. The vapor phase will rise through the column. It will be taken out at the top and then sent to a condenser where it will be cooled, and the resulting condensate is then divided into two parts. One part is taken out as distillate or the top product, whereas the other part is sent back to the column as reflux. The reflux then flows down, adds to the liquid part of the feed on the feed tray, and then again it flows down and the operation continues. From the reboiler, the bottom product or the residue is taken out. Again, the feed plate divides the column into two sections. The section above the feed plate, we call that as rectifying section, whereas section below the feed plate, we call that as stripping section. Okay. Now, in my previous video, I have discussed about different types of feed to a typical tray column in details. Over here, I'll summarize that discussion. There are different types of feeds. The feed to a typical tray column, they can be admitted under or they can be introduced under a variety of thermal conditions. The energy content of this feed could be different. Based on this thermal conditions, you have different types of feeds. The feed types based on its thermal conditions. You have these types: cold liquid, liquid at its bubble point or saturated liquid. Then you have partially vaporized feed. Then you have vapor at its dew point, or you call that as saturated vapor. And finally, you could have superheated vapor. So these are the five types of feed, feeds to a typical tray column. Then when any of this feed enters on the feed tray, the quantities of vapor and liquid on that tray, quantities of liquid and vapor on that tray, they change abruptly. The quantities of liquid and vapor on the feed tray change abruptly as soon as any of these five feeds enter onto the feed tray. Now let us talk about the thermal condition of the feed. So in order to understand the concept, we are going to consider the feed to be a saturated liquid. Saturated liquid, that is, it is a liquid at its bubble point. Liquid which is on the verge of boiling. Actually, it will be a liquid solution, and liquid solution will not have a sharp boiling point. Instead of that, it will be having a bubble point. So we are talking about the feed which is a saturated liquid or a liquid at its bubble point. Now, when saturated liquid is admitted on the feed plate, what happens? It simply adds to the liquid in the stripping section. As soon as it enters on the feed plate, it goes down and adds with the liquid in the stripping section. So we can understand it with the help of this simple schematic diagram. So you have the feed plate. Now the feed in the form of a saturated liquid, it is coming onto this feed plate. So all of the liquid it will be going to the stripping section. Then you'll have there is liquid that is coming from the rectifying section. It will come down and it will add with this saturated liquid. Okay, so the liquid that results in the stripping section, it will be combination of the liquid that is coming from the rectifying section and the saturated liquid that is entering as the feed. Whereas the vapor that is rising from the stripping section, it will be coming to the tray column. Nothing will happen with it, and it will simply rise to the rectifying section. So by looking at this simple schematic diagram, you can easily establish a relationship between L and L bar and then G and G bar. So you can clearly understand in this case L bar is greater than L, because L bar is obtained after the saturated liquid from the feed is added to the liquid that is coming from the rectifying section. That's why L bar will be greater than L. And as far as vapor is concerned, nothing is happening with the vapor phase, with vapor stream. Vapor stream in the stripping section, and the flow of vapor stream in the stripping section is same as that in the rectifying section. Therefore, you have this relation. G bar is equal to G. That is molar flow rate of vapor in the stripping section is equal to molar flow rate of the vapor in the rectifying section. Okay. So that means when you have saturated liquid as the feed, then you have these relationships between L bar and L and G bar and G. L bar is liquid flow rate, molar liquid flow rate in the stripping section. L is molar liquid flow rate in the rectifying section. Similarly, G bar is molar vapor flow rate in the stripping section, and G is molar vapor flow rate in the rectifying section. Okay, now let us continue our discussion on the thermal condition. So I'll use few notations. Let me explain those notation. For feed, F will be its molar flow rate. It could be kilomole per second, for example. Molar flow rate, moles per unit time. XF is mole fraction of the more volatile component in the feed. So for example, if we assume that the feed is a binary solution of A and B, in which A is the more volatile component, that is, A will be having lower boiling point than B, and it will be having a higher vapor pressure than that of B. So if that is the case, then XF represents mole fraction of A in it. In general, XF is mole fraction of the more volatile component in the feed. HF is molar enthalpy of the feed. What is molar enthalpy? Molar enthalpy will be having units, for example, kilojoules per kilomole. So HF is molar enthalpy of the feed. Then L bar, the molar flow rate of liquid. And for this liquid, HLF will be its molar enthalpy per unit mole. So HLF, the notation tells you about the tray from which the liquid is coming. So from this notation, it is clear that it is coming from feed plate, and I'm identifying feed plate by F. So it would be liquid that is coming from plate number F, and its enthalpy will be, its molar enthalpy will be HLF. With similar understanding, molar enthalpy of the vapor stream that is rising, that is coming from the stripping section, will be HGF plus 1. Why F plus 1? Because it is coming from a tray that is next to F tray. And the tray next to F tray is F plus 1 tray. Okay. Now, if you look at the liquid stream that is coming from this rectifying section, it is actually coming from a plate that comes before the feed plate. And obviously that plate will be F minus 1 plate. Okay, so accordingly, for this liquid stream, the enthalpy will be HL F minus 1. Enthalpy of the liquid that is coming from F minus 1 plate. And I'm sure you can now easily tell what will be the notation for enthalpy of this stream. It will be HGF. It is enthalpy of vapor that is rising from F plate. Okay, so I hope the notations are clear to you. If you have any doubt, you please mention that in the comment section. Okay, now let us take overall material balance. We are going to take overall material balance at the steady state. And at the steady state, the overall material balance will be input material is equal to output material. Rate of material in is equal to rate of material out. So the overall material balance will be rate of material in is equal to rate of material out. Okay, and what will be the unit of this terms? It will be kilomole per second. Kilomole per second of material in is equal to kilomole per second of material out. Okay, so let me first erase it so that I can write on the overall material balance. So the overall material balance at steady state, of course, we are going to write it now. So it will be F plus L plus G bar is equal to L plus G bar. So we are writing overall material balance across the feed plate, or for the feed plate you can say. So if you look at the feed plate, which material streams are coming to it? One is the feed and the other one is the liquid that is coming from the rectifying section, and then you have the vapor stream that is coming from the stripping section. So accordingly, the input will be F plus L plus G bar. Whereas the streams that are leaving, the material streams that are leaving the feed plate are, one is L bar and the other one is G. So it will be L bar plus G. Okay, so overall material balance at steady state will be written as F plus L plus G bar is equal to L bar plus G. Okay. Now let us write the energy balance. Again, we are going to write the energy balance at the steady state. That is, rate of energy in is equal to rate of energy out. And the rate of energy will be given, for example, it will be given as kilojoule per second, for example. That is energy per unit time. Okay, so how are you going to write the material balance, energy balance at the steady state? So input energy. Energy comes on the tray along with this streams. The feed stream, the liquid stream that is coming from the rectifying section, and the vapor stream that is coming from the stripping section. So accordingly, you will have F into HF. Now let me explain this term. So F has units of kilomole per second, and HF, it has units of, for example, kilojoule per kilomole. So what is going to happen if you take product of F and HF? This kilomole and this kilomole will be getting cancelled out, and you will be left with kilojoule per second. Okay, so that means each term in this equation, FHF, L into HLF minus 1, each term will be having the units of kilojoule per second. That is energy per unit time. Okay, so I hope this is clear to you. Now let me first erase that so that I will continue my discussion. Okay, so in the next step, if you talk about a single tray, like we are talking about a feed tray. So over a single tray, changes in this parameters, what changes in composition are very small, changes in temperature are very small, and even changes in molar enthalpy are very small. So for a single tray, changes in these parameters are very small. You can neglect those changes. Change in composition, change in temperature, and change in molar enthalpy. That means I can say that molar enthalpy of the liquid that is coming from F minus 1 plate is equal to molar enthalpy of the liquid that is coming from the feed plate. And in general, I will denote that as HL, which is molar enthalpy of the liquid. Same is the case with the vapor phase. Molar enthalpy of vapor coming from F plus 1th plate is equal to molar enthalpy of vapor coming from F plate. And in general, I am denoting that as Hg, that is molar enthalpy of the vapor associated with a single tray. And which tray is that? That tray is the feed tray. Okay, that means in our further discussions, we will be using HL to denote enthalpy of the liquid stream and Hg to denote the enthalpy of the vapor phase or vapor stream. Okay, so let us continue further. Okay, so energy balance, we will continue with the energy balance that was written on previously. So that was FHF plus LHL plus G bar Hg plus L bar HL plus G Hg. Okay, so you must have noticed now enthalpy of liquid will be HL throughout the equation and enthalpy of the vapor will be Hg throughout the equation. And of course, enthalpy of the feed will be HL. It will be different from the enthalpy of the liquid and enthalpy of the vapor. Okay, so let us move ahead. Now we will rearrange this equation. What? I'll bring this term L bar HL on the side and take this term G bar Hg on the other side. So if I do that, I will be having FHF plus LHL minus L bar HL, that is equal to GHG minus G bar Hg. So in the next step, on the left hand side, I can take L common from these two terms, and on the right hand side, I can take on the left hand side, from these two terms, we can take HL common, whereas on the right hand side, we can take Hg common. So if we do that, we'll have FHF plus L minus L bar into HL, that is equal to G minus G bar into Hg. And I'm calling that as equation number 1. Okay. Now, the overall material balance that was written previously, it is F plus L plus G bar is equal to L bar plus G. Now, I will rearrange this equation. I will bring this G bar on this side and this L bar on this side. So, this will be F plus L minus L bar is equal to G minus G bar. Okay. So, at this point of time, I have got equation for G minus G bar, which I am going to use in equation number 1. So, using this in equation number 1, I will be having FHF plus L minus L bar into HL is equal to F into L minus L bar into Hg. Now, G minus G bar is replaced with F plus L minus L bar. Okay, so I'll simplify it further. That is, I'll multiply with Hg to each term in the bracket. So this will be FHF plus L minus L bar into HL, that is equal to F into Hg plus L minus L bar into Hg. Okay, so on in the next step, what I'll do, I will be rearranging that equation. Rather, I have rearranged the equation. So it is now FHF minus F Hg, that is equal to L minus L bar into Hg minus L minus L bar into HL. Okay. Now on the left hand side, I'll take F common out of these two terms, and on the right hand side, I'll take L minus L bar common. So if I do that, I'll be having F into HF minus Hg, that is equal to L minus L bar into Hg minus HL. Okay, in the next step, I'll rearrange the equation further in order to ensure that terms on either side, that is right hand side and left hand side, they are positive. So on the left hand side, I'm interchanging the position of Hg and Hf. So now it is F into Hg minus Hf, that is equal to L bar minus L into Hg minus HL. If you look at this term, Hf minus Hg, that will be negative term because Hg is greater than Hf. Okay? Likewise, since L bar is greater than L, this will be negative. So that's why I have interchanged the positions of Hg and Hf on this side and L bar and L on this side. Okay? Further, I will rearrange and get this equation. Hg minus Hf divided by Hg minus HL, that is equal to L bar minus L divided by F. And each ratio, then I'll be denoting it by a parameter, and that parameter is parameter Q. So now we have Hg minus Hf divided by Hg minus HL, that is equal to L bar minus L upon F, that is equal to Q. And now I am calling this as equation number 2. Okay, so let us continue. Further, we got equation for a parameter, and I'm denoting that parameter by Q, and that was the objective of discussion. Now, objective for today's discussion. So Q now is either Hg minus Hf divided by Hg minus HL. Let us call it as equation number 3. Or Q is L bar minus L upon F. Let us call this as equation number 4. Okay. Now, in this case, the parameter Q, it defines the thermal condition of the feed. So, for each of the feed out of the 5 feeds that I listed previously, Q will be having a particular value. That is, for cold liquid, Q will be having one value. For saturated liquid, Q will be having its one value. I'll be talking about values of Q in my next video. For timing, let us understand that parameter Q is nothing but the parameter that defines the thermal condition of the feed. Now, if you look at equation number 3 and look at the numerator is Hg minus Hf. So, this is difference between enthalpy of the vapors and enthalpy of the feed. That means in equation number 3, the numerator is the heat that is required to convert 1 mole of feed to saturated vapor. Heat required to convert 1 mole of feed from its condition to saturated vapor. Whereas the denominator, which is difference between molar enthalpy of vapor and molar enthalpy of liquid, that is nothing but the molar latent heat of vaporization. That is the denominator in this case. Denominator of equation number 3 is nothing but molar heat, molar latent heat of vaporization. Okay? And in equation number 4, now the numerator, which is L bar minus L, it is simply the moles of saturated liquid that will be resulting in the stripping section once saturated liquid or once feed enters into the column. The numerator in case of equation number 4 is the moles of saturated liquid resulting in the stripping section due to the entry of the feed. Okay, so with this understanding, we are going to use those two equations, equation number 3 and equation number 4, to define the parameter Q. Parameter Q defines the thermal condition of the feed. As per equation number 3, which is Q is equal to Hg minus Hf upon Hg minus HL. So, as per this equation, Q is the heat required to convert 1 mole of feed from its initial condition to saturated vapor divided by the molar latent heat of vaporization. So, in the numerator, you have the heat required to convert 1 mole of feed from its initial condition to saturated vapor, whereas in the denominator, you have molar latent heat of vaporization. Then, if you use equation number 4, which is Q is equal to L bar minus L divided by F. So as per this definition, you can define the parameter Q as the moles of saturated liquid resulting in the stripping section per mole of feed that enters the column, that enters the tray column. That is, as per this equation, Q will be equal to L bar minus L if F is equal to 1. Okay, so if feed is 1 mole, then Q is the liquid, saturated liquid that will be resulting in the stripping section. Okay, so there are two ways in which parameter Q can be defined. So one is the heat required as per equation number 3. This is heat required to convert 1 mole of feed from its initial condition to saturated vapor divided by the molar latent heat of vaporization. And as per equation number 4, this is moles of saturated liquid resulting in the stripping section per mole of feed that enters the tray column. With this, I end my discussion for today. My objective was to talk about the thermal condition, how thermal condition of the feed is defined, and then what is the parameter Q, how it is defined. Okay, so with this, I end my discussion for today. Thank you for being with me. Please, thanks for watching my video. Do subscribe to my channel. Please subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you will be notified as soon as I upload any new video from any new video on my YouTube channel. Thank you. Thank you for being with me. Have a nice day. Bye-bye.